All right, so here's some examples about exponentials and logarithms and that kind of stuff. So let's just simplify this. So the first thing that I don't like is negative powers. One thing you can do is, so of course we know that a negative power is the reciprocal of its positive power. So one thing you can do is if you have a negative power on the top, you can put that on the bottom with a positive power. And if you have a negative power on the bottom, you can put that on the top with a positive power. So these kind of just switch places. So 3 to the 15th over 9 to the 7th. And so let's do it. Let's do 3 times 3 times 3 times 3. Okay, I'm joking. No, we're not going to do that. That would be a huge number, and there's a much easier way to do that. Here's what we really want to do. These have a common base. In other words, 9 is a power of 3. And that would be the smart thing to do here. What I can do is this, because 9 is 3 squared. It's that. And then I know this was one of our power rules. If I have a power raised to another power like this, then what I do is I multiply the two numbers. Where is that? That's on the back of this. Yeah, so I'm doing this rule. I have like a to the b in parentheses, and it's to the c power, and that turns into the a to the b times c. So this turns into 3 to the 2 times 7, so 3 to the 14th. And so I've got 3 to the 15th over 3 to the 14th, and so I subtract them. That would be this rule, that if I have a power divided by another power, then I can just subtract the two exponents. 3 to the 1, which is just 3. So yeah, I mean, I was joking when I said let's do 3 times 3 times 3, 15 times, because of course, yeah, it's doable if you have a calculator, or I guess that this is pretty big number, so you have to have a decent calculator to handle a number this big, but you can do it that way. But you can also do it without a calculator at all by just simplifying it. Simplifying it the smart way, so that you don't have to deal with huge numbers. Okay, so let's simplify this. So this is x squared times, so when you have a product like raised to a power, you can like distribute the power here and here. So this is 3 to the 4th times x to the 4th. And then, okay, 3 to the 4th, well, we are really, and this time there's nothing to cancel it with, so we really just have to do 3 times 3 times 3 times 3, but that's really much better than 3 to the 15th power. 3 times 3 is 9, and 3 times 3 is 9, and 9 times 9 is 81. So 3 to the 4th is 81. And then I'm going to combine the x's, x to the 6th, you add them. Yeah, okay. Let's do log base 2 of 8. So we have a logarithmic statement like this, if and only if a to the c power equals b. This is basically what the logarithm question is asking you. It's asking you, what power do I have to put on the a to get b? And the answer to that question is the logarithm base a of b. In other words, c is that number. C is that number that if you put it on top of the a, you will get b. In other words, a to the c power equals b. So if I want to figure out this number, I can call it c, and then convert this logarithmic statement into an exponential statement. What that means is this number to this power equals this number. And now you want to look for a common base. Of course, 8 is a power of 2. 8 is 2 cubed. And now you can just match the c, because you have 2 to a power equals 2 to another power. You can just match the c to this power. So the log base 2 of 8 is 3. Let's do another one of those. Log base 9 of 27. I can call that number c. So that would be like 9 to the c equals 27. And now I can do the same thing, except last time we had 8 was a power of 2. 27 isn't really a power of 9, right? Well, I mean, it's not a whole number power of 9. 9 to the 1 is just 9. 9 squared is 81. I can't think of what power I would put on top of a 9 to get a 27. But that's why you look for a common base. It's not always that this number is the common base. What you look for is that the common base should be a number that, like this is a power of the common base, and this is also a power of the common base. The common base here is going to be 3, because this is a power of 3, and this is a power of 3. This is 3 squared. This is 3 cubed. So this is 3 to the 2c, and this is 3 to the 3. So I match the powers. 2c equals 3. So finally, c equals 3 halves. So the log base 9 of 27 is 3 halves. All right. Let's solve some equations now. Equations involving exponents and logarithms. So we'll start kind of easy. Let's just do 2 to the x equals 3. I would recommend doing the logarithm of both sides. And you can do a couple of things. I could do the log base 2 of both sides. And the reason why I'm doing that is because the logarithm and the exponent function are inverses. So as we talked about, this basically cancels and I just get x. X equals log base 2 of 3. Here's a slightly different thing you can do. And so the first thing I did was I did the logarithm base 2, and I chose that just because the base of this was 2. And that can be a smart choice. But for various reasons, as we do calculus, we're going to do everything in natural logs. So what I could have done is I could have done the natural log of both sides. And then what can happen is I can bring the x down because that's a logarithm rule. So x ln 2 equals ln 3. And then ln of 2 is just a number. I think it's about 0.6. but it's just a number. So this is x times some specific number equals some other specific number. And how do we solve an equation like that? I just divide by the number that I want to get rid of. So I get ln3 divided by ln2. So we got the answer. These don't look the same. They are the same. They just don't look the same. Well, they look the same to me because I see through it, and maybe you see through it too. But let me, in case you don't, let me remind you. Here's the change of base formula. Log base a of b equals log base c of b over log base c of a. So if I start with this one, and what this formula does is it takes a logarithm of one base and it converts it to logarithms of another base. So here I've got a log base 2, and let's convert it to log base e, or natural log, and that's what would make sense because that's what we're looking at over here. If I use the change of base formula to convert this, I would do the natural log of b, which is 3 here, so I get the natural log of 3, and I would divide it by the natural log of a, which is the base here, so that's why there's a 2 there. So this number and this number are the same thing. We did not get two different answers. It's just two different forms of the same answer. All right. And by the way, personally, I don't have a strong preference which one of these you give me. I'll accept either one, unless I specifically state I want it in a certain form. All right, let's do another one. So this one is almost the same. It just involves like a couple of other easy steps first. So the x is in here, so I want to get this by itself. The first thing I want to do is get rid of that -7. So 3 times 5 to the x equals 17. And so 5 to the x equals 17 thirds. So if I did the log base 5 of both sides, I would just get x equals log base 5 of 17 thirds. And I guess I haven't been doing the arrows, but I'll do it on this one. All I did to get from the first step to the second step is add 7 to both sides. That's an if and only if step. And then I multiplied both sides by a third, which is not 0, so that's an if and only if step. And then I did the log of both sides. I'm doing a log base 5 of both sides, and logarithms are one-to-one functions, so this statement is if and only if this statement. So I am confident that I got all solutions and that everything that I found is a solution. Let me do another one. This one's almost the same as the last one, except it's a -10 instead of a 10. So let me go fast here. This is if and only if 3 times 5 to the x equals -3. Multiply both sides by a third. 5 to the x equals -1. And then I would do the log base 5 of both sides. But then I've reached a nonsensical statement. X equals log base 5 of -1. -1 is not in the domain of log base 5. You can't do the logarithm of a number unless it's a positive number. I couldn't even do the log of 0. I definitely can't do the log of a negative number. It has to be a positive number. So what I conclude here is that there's just no solution. Like this thing that I wrote that kind of vaguely looks like a solution until you examine it more closely and realize that it doesn't make sense, this doesn't count as a solution. And that's okay. Some equations have no solution, just like problems in life. Let's do part D. This time I'm starting with an equation that has logarithms in it. If you noticed, for parts A, B, and C, the original equation didn't have any logarithms. The original equation had exponents. Now we have an equation that starts with logarithms. But it's not that bad. So x appears here. Let's try to get the x by itself. I'm going to subtract 3 from both sides. And that's an if and only if step. I'm going to multiply both sides by a half. That's an if and only if step. And then I'm going to, well, how do I get rid of this natural log? Remember that exponentials and logarithms are inverses. So the way you get rid of an exponent is, well, roughly speaking, the way you get rid of an exponent is with a logarithm, and the way you get rid of a logarithm is with an exponent. So more formally, what does that mean? I'm about to apply a function to both sides. The function that I'm going to apply to both sides is the inverse of natural log x. The inverse of a logarithm is the corresponding exponential function. And since this is log base e, its inverse is e to the x. So I'm going to do this function to both sides. What does that really mean? I'm doing e to this power and e to this power. And this basically cancel. And I just get x equals e to the minus 5. It's okay to do e to the minus 5. Exponential functions, as we talked about initially, exponential functions have a domain of all real numbers. So you can do e to a negative power. You can do 2 to a negative power. That's all okay. And I can't really simplify this any more than it is. E is this kind of ugly number that's like 2.7, blah, blah, blah. It goes on forever. So I'm not going to be able to really simplify this. I'm just going to call it good. And by the way, I went kind of fast on the arrows. Some of these steps were easy, like when I'm just subtracting 3 from both sides, when I'm multiplying both sides by a half. This step in particular, this is if and only if, because what I did was I applied a one-to-one function to both sides. The function that I applied to both sides is the e to the x function, and exponential functions are one-to-one. So I'm confident that everything that I found is a solution. And I'm emphasizing this because we're about to do an example where it's not going to be so easy. I'm going to go through the steps. I'm going to arrive at some solution, or some, I shouldn't call them solutions, but some numbers, and I'm not going to be confident that they are all solutions. Let's get to that. I've got this one. So what is different about this one? First of all, x shows up in 2 places. There's an x here and an x here. It's nicer if x only appears in one place, like in all the examples that we did before. And if you look at the original equation, x was just appearing in one place here. X just appears one place here. You know, even in the last one we did, x only appears here. And when you have that, you can just start, I mean, your objective is to get x by itself, so you can just start kind of looking at the stuff that's around x and getting rid of it. Do the steps you need to do to get rid of the stuff that's around the x, and then x will be by itself. So what do we do in a situation like this? It's more complicated. One thing I would recommend is using log rules to combine logarithms. So where did that go? Yep, here we go. Like these log rules. So what I have here is I have logarithm. I mean, it's nice that I have the same base, so it's log base 2 both places. So let me mention that first. And other than that, I have the logarithm of one thing plus the logarithm of another thing. And that's like this rule. So it's like I have the right side of this equation, and what I can do is I can convert it to the left side of this equation. In other words, I can convert this to log base 2 of this times this. And as I take that step, let me point something out here. These rules have rules that go with them. This rule that I just applied only works if the numbers that I'm doing the logarithm of, b and c, are both positive. So what I can do here is, I think the way I want to phrase this is I'll put if and only if, and then I'll write this equation together with the assumption that I'm only ever doing the logarithms of positive numbers. If I didn't put this part, then this would not really be if and only if. I have to assume that I'm only doing the logarithms of positive numbers in order for this to work. But let me proceed. Now what I would do is I would like to just get rid of the logarithm. I've got the log of one single thing equals 5, and so I'm about to apply the same function to both sides, and the function that I'm going to apply to both sides is the inverse of log base 2. In other words, I'm going to apply the function 2 to the x. 2 to the x is the inverse of log base 2. So yeah, maybe I should have put brackets around this just to make it clear that, just to make stuff more clear. So I applied the function 2 to the x to both sides. So I've got 2 to the this power and 2 to the that power. This is all still assuming that these numbers that I was originally doing logarithms of are positive. So what happens? I can simplify this. Of course, the reason why I did this is that these cancel. All I get is I get the number inside. So I get x plus 1 times 3x minus 1 equals. And here I've got 2 to the 5th. That's not terrible to do. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 35. 32, sorry. 2 to the 5th is 32. And we are still assuming this stuff. And now let me tell you how the rest of this is going to go. It's basically a quadratic equation. I'm going to multiply this out. I'll have some x squareds and stuff like that. I can move everything to one side, and then You know how we solve quadratic equations. Usually we end up trying to factor it. In the worst case scenario, we use the quadratic formula, but it's a pretty standard procedure that we're about to follow. So let me FOIL this out first of all. I've got a 3x squared, and I would have a negative x from the outer, and I would have a positive 3x from the inner. So let me put plus 2x. This 2x is the result of a negative x and a 3x. And then if I do the last, I've got a 1 times a negative 1. So that's this. And of course, I carry down this assumption. Yeah, so like I said, we've got a quadratic equation. Let me just do an easy step here where I move this over. And now, well, some of you may have good factoring skills where you can factor this. I find it easier to just use the quadratic formula, like, because what I don't like is I don't like this 3 in front. I'm good at factoring quadratics if it's just plain x squared. I could think of dividing everything by 3, but not everything's divisible by 3. Like then I'd have to deal with fractions, and that annoys me too. So if you know how to factor these things, that's great, but I'm not going to go over that again because it's not strictly a necessary skill for us to have. Let's go to the quadratic formula. I guess I should go ahead and write down the formula just for everybody's convenience, as long as I can do it without making a mistake. There we go. So in this case, it would be negative 2 plus or minus the square root of 4 minus 4 times 3 times negative 33. Over 2 times a, which is 2 times 3 is 6. Carry down my assumption. Simplify. So here I have some annoying big numbers here, but let me try to be smart about this thing that's underneath the square root. And one of the valuable things I can hopefully teach you is to just how to do things by hand without using a calculator. I can factor a 4 out of this. If I factor a 4 out, what I'm going to have is a 1 and then minus 3 times negative 33. So there's a double negative, so that's going to turn into a positive, and then 3 times 33 is 99. And that's pretty nice. This is actually just 4 times 100, so this is the square root of 400. Square root of 400 is 20. Negative 2 plus 20 over 6 would be 18 over 6, which would be 3. Negative 2 minus 20 over 6 would be negative 22 over 6, which is, I guess, negative 11 thirds. So where are we now? Like I was warning you about, we have arrived at a list of numbers. It's not a long list. There's just 2 numbers. One of them is 3. The other one is negative 11 thirds. And before we go ahead and just call those our solutions, let's think. Well, so technically this looks like a long string of if and only ifs, but that was only because I carried this extra assumption down all the way. All you have to do in the end is make sure that the numbers that you came up with satisfy the assumption. Anything that doesn't satisfy the assumption is going to get thrown out, and anything that does satisfy the assumption is going to be a genuine solution. So let's check x equals 3. The assumption is that x plus 1 has to be positive and 3x minus 1 has to be positive. Sure enough, 3 plus 1 is positive. And the other thing was 3x minus 1, so let's check that. So 3 times 3 minus 1 is 8. Sure enough, that's positive. So x equals 3 is a solution. Let's check x equals negative 11 thirds. Negative 11 thirds plus 1 is positive. No, it's not. If we get a common denominator, 1 is like 3 thirds, so this would be negative 8 thirds. This is not a positive number. That's why we check. By the way, just to introduce a little bit of terminology, there's a name for this. This is called an extraneous solution. The word extraneous, roughly speaking, kind of just means not real. It's not an actual solution. It's a number that arises from the procedure, but the final, it's like a number that arises from the procedure and persists until the very end when you check that it satisfies something, and then it turns out that it doesn't. Yeah, I mean, extraneous, you look at the word and you see the extra in there, but this is like extra in a bad way. It's extra like you don't need it, you don't want it. Not extra like, the good kind. So, right, in the end, what do we have? We had one genuine solution and one extraneous solution. So this is all genuine solutions, just x equals 3.